Working paper times companion to the wet quarry method. On the buoyant hull ancient Egyptian pyramid construction, the complete buoyancy budget. Hollowing, bladders, an underbase pontoon raft, salted water, and a bank of N counterweight stones on ropes, every lever this theory has proposed, unified into one force balance and checked, honestly, against the Great Pyramid's own numbers. Author Aaron Cattell Method Archimedes Principle plus Masonry Arch Statics plus Rope Pulley Statics Case Study Great Pyramid Giza B equals 230.3 m H equals 146.6 m. This paper tests engineering questions in isolation against real dimensions and known scan data. It is a feasibility check on part of a larger working theory, not a claim about how the pyramids were actually built. Abstract. Flotation is a force balance, buoyancy pushes up, weight pulls down, and anything else pushing or pulling on the structure, including rope tension from a sinking counterweight, is a legitimate third term in that balance, not a separate problem. We derive that term properly, generalize it to any number of counterweights of any size, and show that yes, tension pulling up genuinely reduces the buoyant volume required elsewhere. The catch is a matter of scale. Matching a meaningful share of the load this way needs counterweight mass on the same order as the pyramid itself, which is dramatically less material efficient than simply building more raft. The right role for counterweights turns out to be a free bonus from construction waste, not a primary mechanism, and folding every lever in this paper together, at last, into one build sequence, gets the numbers as close to plausible as this analysis is able to take them. Section 1. The flotation condition. An object floats when the upward forces on it equal the downward ones. Until now that's meant buoyancy alone. Fluid GV displaced greater than or equal to stone phi Vg. A rope pulling up on the structure is just a second upward force added to the same balance. Nothing about the physics requires that force to come from displaced water. Buoyancy plus tension greater than or equal to weight the complete force balance. Section 2. Applied to the Great Pyramid. Khufu's base B almost equal to 230.3 m, height H almost equal to 146.6 m, base area A almost equal to 53,052 square meters, perimeter P almost equal to 921.2 m, enclosed volume V almost equal to 2,592,000 cubic meters, as-built phi almost equal to 0.97, stone mass almost equal to 6,285,600 t. Section 3. Raising the fluid, salt and brine. Salt raises fluid up to a solubility ceiling near 1,200 kilograms per cubic meter for saturated brine. Max alone climbs from 0.40, freshwater, to 0.48, saturated, real, but capped well short of 0.97, and a one-time cost of roughly 800,000 tons of salt for the whole basin. Section 4. Pontoons via undermining. A single sealed timber raft, slid under the finished, still solid pyramid using the same undermining technique, already proven, on individual quarry blocks. At phi almost equal to 0.97, matching the real, scan structure, the raft alone needs to run roughly 45 to 70 m thick across the whole base, depending on salinity. Section 3. Section 5. The general buoyancy budget, with tension. Let beta and gamma be bladder, and raft volume as fractions of V as before, and add a fourth term, delta, the total mass of all counterweights expressed as a fraction of one full pyramid mass of stone, delta equals mcw a stonev. Writing the force balance out in full and dividing through by stonev. Max, beta, gamma, delta, fluid, equals fluid stone, times 1 plus beta plus gamma, plus times 1 fluid is stone, complete flotation limit, all 5 levers. The first term is everything from Section 1 Section 4, hollowing, bladders, the raft, scaled by fluid density. The second term is new. Every unit of counterweight mass contributes 1 fluid is stone of itself as usable lift, exactly the fraction of a submerged stone's weight that isn't cancelled by its own buoyancy. Setting delta equals 0 recovers every result from section 3. Section 4 unchanged. Section 6. The counterweight system, properly derived. Take the sketch setup. A rope runs from a counterweight stone, up over a fixed point. A gantry or tower anchored to solid ground at the pit's rim, not to the floating pyramid itself, and down to an attachment on the pyramid. Once the counterweight's own small starter pontoon is burned away, the stone hangs from the rope by its submerged weight alone. T equals mcg, 1 fluid is stone, tension from 1 counterweight. Ideal frictionless pulley. Yes, this genuinely reduces the buoyant volume required. Tension pulling up on the pyramid is exactly as good, force for force, as an extra cubic meter of displaced water. The force balance in section 5 already accounts for this properly. Every newton of T is a newton the raft, section 4, no longer has to supply. Nothing in this analysis is special about the number 4, or about equal-sized stones. For n counterweights of arbitrary individual mass mi, the total assist is just their sum. Total equals mg, 1 fluid, stone, equals mcwg, 1 fluid is stone, n counterweights, any sizes, only the total mass m_cw matters. That's a genuinely useful practical result. It doesn't matter whether the mass is arranged as 4 large blocks, or 40 small ones scavenged from odd-sized quarry offcuts. Only the total counterweight mass, summed across however many stations there are, determines the lift. Force balance on the floating pyramid, weight W equals phi_stone, Vg buoyancy Bt_1. T_n, pulling up, from n fixed points B plus T greater than or equal to W less B needed, the more T supplies. Figure 1, buoyancy and rope tension are additive upward forces against the same downward weight. Any number of counterweight stations, of any size, contribute to the same sum T. Section 7. How much counterweight actually matters. Solving section 5's master equation for delta shows what it would take for counterweights to replace the raft entirely. Phi equals 0.97, no raft, freshwater. Delta equals 0.97, 0.40, 0.60 equals 0.95 counterweight mass needed, as a fraction of the pyramid's own mass. Delta equals 0.95 means roughly 6.16 million tons of counterweight stone, essentially another pyramid's worth of quarried material, hung on ropes. Counterweights alone cannot replace the raft. The scale required is the same order of magnitude as the structure they are lifting. Used as a supplement instead, smaller amounts of counterweight mass do meaningfully shrink the raft. Blending with saturated brine, fluid equals 1,200 kilograms per cubic meter. Counterweight mass, delta. Tons of stone. Raft thickness needed. Source. Delta equals 0, no counterweights. 0. 49.9 m. Delta equals 0.05. 324,000 t. 47.2 m. Plausible as quarry waste of offcuts. Delta equals 0.30. 1,944,000 t. 34.0 m. Dedicated new quarrying. A modest, free allocation, delta equals 0.05, sourced from material already being cut as waste during construction, buys a real, but small reduction. A large, dedicated allocation, delta equals 0.30, buys a much bigger one, but at the cost of quarrying nearly 2 million additional tons of stone purely to hang as ballast, which raises the question section 8 answers directly. Section 8. Material efficiency. Raft versus counterweight. Both the raft and the counterweights ultimately cost labor, measured in tons of material quarried, shaped, and moved. It's worth comparing what each ton actually buys in lift. The raft is mostly air. A thin timber shell encloses a huge sealed volume. For the saturated brine raft in section 4, 2,646,000 cubic meters enclosed, almost equals 21,300 tons of 0.15 m timber planking. Efficiency raft equals fluid raft, timber almost equal to 149 kilograms, lift per kilogram of timber material efficiency raft. A counterweight stone is solid throughout. Every kilogram quarried only returns the fraction of itself not cancelled by its own buoyancy. Efficiency equals 1 fluid stone equals 1,200 divided by 2,500 almost equals 0.52 kilogram lift per kilogram of stone material efficiency, counterweight. Lift returned per kilogram of material used timber raft almost equal to 149. 1 stone counterweight almost equal to 0.521. Figure 2. Roughly a 286-fold difference in material efficiency. A ton of timber shell outperforms a ton of quarried counterweight stone by close to 3 orders of magnitude. What this settles? Counterweights are not a competitive way to generate bulk lift. Building more raft is nearly 300 times more efficient per ton of material handled. Their honest role is exactly the free case in section 7. Mass that's already being cut as quarry waste, hung on ropes at no marginal quarrying cost, is a small bonus worth taking. Deliberately quarrying dedicated counterweight stone is not. It would be cheaper, in every sense, to simply build a slightly thicker raft. Section 9. Bladders at block scale. Unchanged from the companion sections, a 1 cubic meter, 2,500 kilograms block needs about 1.5 cubic meters of bladder volume in freshwater, almost equals 1.08 cubic meter in saturated brine, 6 or 4 hides respectively. This remains a per block tool used during quarry transport, separate from the final full pyramid float. Section 10. The arch as load redirector. Any void in the raft, or in relieving chambers, still needs an arch to stay open under load. H equals WL squared, 8 hours, crown thrust. E x, less than or equal to T, x, 6 middle third rule. Mu greater than or equal to tan, psi, no slip condition, dry limestone mu almost equal to 0.6 to 0.7. Thrust line through an arch thrust line. Figure 3. The thrust line must stay within the middle third of the ring's thickness. Section 11. Stress at the raft. P equals W, A almost equal to 1.1 M average base pressure. Small relative to limestone's compressive strength, but the raft now also carries the counterweight anchor loads, section 6, at its perimeter attachment points, another set of concentrated stresses, to check alongside the arch abutments, section 10. Section 12. Every method, combined. Bringing every lever in this paper together, at the allocation, that gets the most out of each, without overreaching any single one. Mechanism. Role. Contribution. Internal hollowing. None, phi stays at 0.97, matching scan data. 0. Bladders. Per block transport aid, quarry to site. Almost equal to 6 hides a block, not part of final float. Saturated brine. Multiplies every other term. Underscore fluid. 1,200 kilograms per cubic meter. Waste stone counterweights. Free bonus, no dedicated quarrying. Delta almost equal to 0.05 raft, minus 5%. Underbase pontoon raft. Primary buoyancy source. Almost equal to 47 m thick, undermined into place. This is the most internally consistent version of the theory this paper has produced. No internal void that scans would contradict. A raft doing the overwhelming majority of the work, because it's by far the most material-efficient mechanism available as Section 8. Salt easing that raft's burden by roughly a third, and counterweights contributing only what construction waste provides for free, never a dedicated, resource-competing operation of their own. Ground-level saturated brine raft almost equal to 47 m, relieving arch counterweight tower backfill. Figure 4. Every mechanism in this paper in one cross-section, the flooded, salted pit, the raft slid underneath by undermining, a relieving arch inside the stone, counterweight towers with ropes running from a sunk, fire-release stone up over a fixed pulley to the pyramid, and backfill closing the pit around the finished structure. Section 13. Sequencing. Build solid, as in the companion paper. At completion, undermine and slide in the raft, Section 4. Salt the basin, Section 3. Attach counterweight ropes to fixed towers at the rim, loaded with quarry waste, Section 7. Flood fully. The raft supplies the bulk of the lift. The counterweights, once their small starter pontoons burn away, add a final, modest assist and, as in the earlier paper, double as the trim system once the structure is afloat. Section 14. Verdict. Does pulling up reduce the buoyancy needed? Yes, unambiguously, this was the right question to ask, and the force balance in Section 5, Section 6 confirms it directly. Tension and buoyancy are additive, so more of one always means less needed of the other. Can more, differently sized counterweights solve the problem? Mathematically, only total mass matters, Section 6, so yes, any number or mix of sizes works the same. But solving the whole gap this way needs a second pyramid's worth of counterweight stone, Section 7, and at roughly 1/286 the efficiency of the raft, Section 8. It's the wrong tool for bulk lift, however it's divided up. What's the right combined design? The raft carries the load, salt eases it, bladders help only at block scale, counterweights contribute only what's free, Section 12. Every method has a role, just not an equal one. In short, the question behind this paper was a genuinely good catch. Rope tension is real lift, not a separate mechanism, and the mathematics bears that out cleanly. What it exposes, once followed all the way through, is that some of this theory's proposed mechanisms are worth a great deal, the raft, and others are worth a little, counterweights, bladders, salt, and knowing which is what makes the combined design in Section 12 the most defensible version of this idea so far. On the Buoyant Hull, working paper by Aaron Cattell, Companion 2, The Wet Quarry Method. On the Buoyant Hull, Ancient Egyptian